Hi, I would like to introduce our work, CLIO, enabling automatic compilation of deep learning pipelines across IoT and cloud. Emerging advances in low-power sensor devices equipped with rich sensors, such as cameras and microphones, present significant computational challenges for machine learning at the edge. This is partly due to the volume of data that needs to be processed, and partly due to the complexity of deep learning models that are needed for processing richer modalities like images, audios, and videos. This is an option that people use to deal with the computational complexity of deep learning models when deploying models on IoT devices. As we can see, as the model compression ratio increases, the accuracy drops. This is another option that people uses to deal with a volume of data when transmitting all the pre-processed data to the cloud for further inference. We could also find out that we achieve a higher data compression ratio by sacrificing the accuracy. While an alternative to local processing may be to transmit raw data or pre-processed data to the cloud for further inference, the main challenge is dealing with limited and variable wireless bandwidth. Bandwidth on low-power radios can be limited and change rapidly, so we need to find ways to be able to gracefully deal with bandwidth changes without compromising inference performance. We bridge the gap by an automatic compilation framework that leverages both local and remote resources to optimize execution of deep learning models while fitting to network dynamics. Our insight is that there are two complementary methods for machine learning under resources constraint. When bandwidth is limited, data compression is used to transmit reduced data to the cloud for process, and when computation is limited, model compression is used to reduce the model size to fit into available resources. What we do CLIO is to simultaneously leverage both model compression and data compression so that we can find the optimal way to take a large deep learning model and partition it to deal with resources constraint and variations in bandwidth. This is the overview of our automatic compilation pipeline. From the user's perspective, we only need predefined models and system metrics such as target latency, energy, or throughput. CLIO will automatically partition the model into different parts and use progressive slicing to deal with the network dynamics. We use a layered deep learning model as an example to introduce our design. CLIO splits the deep learning model so that IoT devices will execute the early layers and local compute and network bandwidth will be utilized efficiently. But partitioning alone does not solve the problem of dealing with variable bandwidth. Unpredictable network dynamics is always a challenge, as we either suffer from a large latency than expected for transmitting the full intermediate features, or tolerate a much worse performance if we execute directly using partial data. However, this model partitioning allows us to manipulate the intermediate features of the deep learning models so that we can fit into available bandwidth. CLIO enables the intermediate features to be progressive, so that when the network fluctuates and the cloud only receives limited partial data, the performance can degrade gracefully. CLIO enables the model to learn ordered feature map, which we call progressive slicing, so that the feature maps can be transmitted in a progressive manner. You can see the example on the right. Why do the ordered feature maps make sense for the network dynamics? For example, for each slice of the feature map, we have a corresponding head deployed on the cloud. When we transmit the intermediate feature map slice by slice and only one slice is received due to the network dynamic, the specific model split will be used for further inference. then the inference latency remains unchanged, while the performance of the partial data will be good enough. We extend the benefits of progressive slicing by adaptive partitioning. For different network conditions, the best points to partition the model may be different, and the adaptive partitioning allows us to adapt the partition points so that we can adapt to long-term wireless variations. Here is a formation of our progressive slicing. The layer deployed on the IoT devices will be f theta x, and the intermediate features will be OK. The progressive slicing will slice the intermediate results OK into different slices denoted as OK from 1 to I. And we will use the slice as input for the headed layers on the cloud. The headed layers on the cloud is denoted as G phi I, and the final prediction output will be hat yi. Then the total objective function will be the sum of the loss functions from the different prediction results. For example, here the objective function will be lyn hat y1 plus lyn hat y2 plus lyn hat y3. And we can simply extend the objective function to a general form of n different slices, as you can see on the right. Also, we use a curve of the progressive slicing to form the envelope of the best accuracy. For each bandwidth, we use the validation data to determine what is the best partition point and slice based on profile bandwidth. And during runtime, we will use the average historical bandwidth to choose the best partition point and slice. This is the overview of our whole system. Since our method is totally compatible with model compression, model compression can be used to compress the user predefined model at the beginning. For the model, we could choose several potential partition points. We will then apply the progressive slicing to the layer right before the partition points. Then we can construct the envelope based on the different partition points. We could deploy all the early layers on IoT devices, and during runtime, we will use a bandwidth estimator to estimate the average historical bandwidth, and based on the estimate bandwidth, we could adaptively choose the best partition points. We compare our methods with progressive JPEG. Our methods could progressively transmit slices, while progressive JPEG could progressively transmit the raw data. For the same latency, we find out that our methods can achieve better accuracy compared with progressive JPEG. Also, when the network dynamics occur, our methods can also degrade more gracefully than progressive JPEG. We also compare our methods with local execution. We could see that our methods could be better than local execution in the medium range of the latency, and for the extreme low latency, we could not achieve better accuracy than local execution. We also compare our method with baseline JPEG. Both baseline JPEG and our adaptation partitioning requires the estimation of the historical bandwidth. For baseline JPEG, it requires estimated bandwidth to compress the data with different qualities. Our comparison is based on the synthetic traces where we change the variance of the network dynamics manually. As we can see, CLIO with adaptive partitioning could achieve the minimum difference of accuracy result from the estimated bandwidth and the real bandwidth. And we could also have the best performance for different variants of the network dynamics. On the real traces, we could see that by introducing the adaptive partitioning, we can achieve a higher accuracy when the bandwidth dynamics occurs, because we choose the best partition points by adaptive partitioning. Another thing that we wish to evaluate is when CLIO will be better for different hardware settings. And as we can see, the regime where CLIO is better lies in between the two empirical methods of JPEG compression and model compression. CLIO is more efficient in different regimes depending on available compute and bandwidth resources. In summary, CLIO is an automatic compilation method for low-power IoT devices that progressively partition a deep learning model between IoT and cloud to optimize latency and energy while also being resilient to bandwidth dynamics. CLIO is a departure from prior work as CLIO operates in a progressive manner and simultaneously reason about model compression and data compression. We have a complete implementation of CLIO on the gapped low-power neural accelerators and have also made the code available. Thank you.